Okay, Advanced Algebra Trig. Here's our first flipped lesson of the year, so we'll see how it goes. Kind of exciting. Okay, 10 boxes here. We're talking about arithmetic sequences and sums of arithmetic sequences. So in the first box here, I've got a picture of a mosaic trapezoid. It's kind of a cool little picture. What I want you to do is just guess the number of tiles it took to complete this and write it on the left-hand side there. Just any old guess. Is it 50? Is it 100? Is it 9,000? Whatever you think it is. Put a guess for the number of individual tiles it took. Okay, you have your guess on the left-hand side there. Just keep it on the left-hand side. We'll come back to it. Okay, let's talk about an arithmetic sequence. An arithmetic sequence is nothing more than a sequence. Is nothing more than a sequence with a common difference. So here's an example of one. Let me give you an example. If I gave you 3, and then 5, and then 7, and then 9, and then 11. Okay, let's examine this, right? Well, to go from 3 to 5, you got to add 2. To go from 5 to 7, you got to add 2. From 7 to 9, you got to add 2. From 9 to 11, you got to add 2. So this number, this difference here is remaining a constant, right? So to find the difference, you pick any term you want, let's say, I don't know, the third term, and you subtract it from the second term, you always get 2. 7 minus 5 is 2, 5 minus 3 is 2, 11 minus 9 is 2. So that common difference right there, for us in this first part here, this would be a value of 2. That's what makes the sequence arithmetic. We keep adding the same value every single time. So one cool thing about an arithmetic sequence is that they are recursive, which means that there's a pattern going on here, right? So we can find the next term by knowing something about the last term. And in fact, the formula, right, the next term, a sub n plus 1, is just equal to the previous term, which is a sub n, plus that common difference d. That's how we get to the next term, right? So if I wanted the sixth term, I would take the term before it, which is the fifth term, so 11, plus the common difference of 2, and that would give me a 13. So sequences are arithmetic. Okay, here's an example. Show that the sequence is arithmetic. A sub n equals 3n plus 5. Well, again, if I take 1 and plug it in, 3 times 1 is 3 plus 5 is 8. So this gives me 8. Taking a 2, plugging it in, 3 times 2 is 6, and 5 is 11. And then plugging a 3 and plugging it in would give me a 14, and so on down the line, right? And a sub n is just 3n plus 5. Okay? So it looks to me like I have to go up 3, and then again up 3. So I would guess that my common difference is equal to a 3 here, and I'm pretty sure it is. But it does say show that the sequence is arithmetic, so let me show you how to do that. Okay? So what we want to do is we want to take a sub n plus 1 and subtract it from a sub n, and we want that to always equal our common difference, which in this case is, we're guessing, a 3. Alright, so what's the value of a sub n plus 1? Well, it's 3 times n plus 1 plus 5. See, all I'm doing is that's substituting an n plus 1 for my n. I'll show you again. I'm substituting an n plus 1 for my n. Alright, so then I'm going to subtract a sub n, which is just 3n plus 5. And hopefully that should equal my common difference, which I'm guessing is going to be a 3. Okay, using the distributive property, I get 3n plus 3 plus 5 minus 3n plus 5 equals my common difference. Well, notice here 3n minus 3n goes away. That tells me I've got... and then I've got 3 plus 5 is 8. So I'm left with 8. And then... oh, so look at that. I forgot to do the distributive property. Minus 5 right there. Minus 5, which gives me a 3. Yikes, don't forget to do that. So I've got negative 3n minus 5. So 8 minus 5 gives me 3. There we go. So that matches with my common difference. That right there is the proof that shows that this arithmetic sequence has a common difference of 3. Don't forget your distributive property there. Yikes. Okay, let's take a look at these here. Is the following arithmetic? Yes, no, why, or why not? Alright, so why don't you head... okay, let's examine, right? To go from 3 to 2, I have to subtract 1. To go from 2 to 1, I have to subtract 1. To go from 1 to 0, I have to subtract 1. So all of those are constant. If I pick any term, say the third term, and I subtract it from the previous term, 1 minus 2 is negative 1. 2 minus 3 is negative 1. So I would say yes, this is an arithmetic sequence, and the common difference is negative 1. Let's go on to B. Right? To go from 1 to 2, I got to add 1. To go from 2 to 4, I got to add 2. So right away, something is telling me that this sequence is not arithmetic because it does not have a common difference, right? And then to go from 4 to 8, I got to add 4. So this is definitely not arithmetic. Remember, in order for it to be arithmetic, it has to have that common difference. So B does not have that common difference. All right, here's one of my favorite things about arithmetic sequences. This is what I call the fast-forward formula, right? So let's say I give you we talk about this sequence here. Let's talk about 8, 11, 14, 17, blah, 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 all the way out, right? So the question would be then, since it's recursive, I can get the next term just by looking at the previous term and then adding the common difference. But what is the 23rd term? Do I really have to go all the way out to the 22nd term just to get the 23rd term? And of course, to get the 22nd term, I need the 21st term, and you can see how this is going on and on and on, right? Well, it turns out that I can just sort of what I call fast forward up to the 23rd term by taking advantage of the fact that my sequence is adding the same value every single time, that common difference, right? So let's see here. What is that? To get from 8 to 11, I got to add 3. Add 3. To get from 11 to 14, I got to add 3. To get from 14 to 17, I got to add 3. So it looks like any term minus the previous term is going to give me a value of 3. So I'm guessing that my common difference is a 3. Right? Well, it turns out that the fast-forward formula, any n term you want, so a sub n, is equal to the very first term plus n minus 1 times that common difference. So this is really, really cool. All right, let's apply that. So what do I want here? I want a sub 23. So what is the 23rd term? Well, it's equal to the first term, which happens to be 8 in this case, plus, now here's what you want to notice, right? This n right here matches that n right there. So I'm going to have 23 minus 1, and then multiplied by my common difference. My common difference happens to be a 3. So that's going to give me 8 plus, well, 23 minus 1 is 22 times 3. So that means I have 74 all the way from my 23rd term. And I did not need to find all the stuff in between. I just took advantage of the fast forward formula. Okay, let's try an example here. Let's find the 15th term for this arithmetic sequence. The first term is 2, the second term is 6, the third term is 10, all the way out to the 15th term. That's the question mark, right? Okay, so again, use the fast forward formula. A sub n is equal to a sub 1 plus n minus 1 times d. The term that I'm looking for is the 15th term. So that means a sub 15 has to be the first term, which happens to be 2, plus n minus 1, so 15 minus 1, times my common difference. Now, it looks like my common difference here is up 4, so I had to figure that out ahead of time. So that means the 15th term must be 2 plus 14 times 4. So that must give me a grand total of, this is 2 plus 56, it looks like. So that is equal to 58. So I can fast forward all the way up to the 15th term because I can take advantage of the fast forward formula. Very, very useful. Make sure you got that on the side there. That's what I call a basic example for this one. Okay, let's go on to a more challenging example where we use the fast forward formula again. So here's a more difficult example. It's asking us to find the first term and the common difference. And all they give us is that the 8th term is equal to 75. Okay, so because this is arithmetic, and we are given the fact that it's arithmetic, here's what we have going on, right? We have a sub 1, we have a sub 2, a sub 3. Let's skip up. we have a sub 8. Whoa. Let's skip up a little bit more, and we have a sub 20. All right, here's what we know. We know that the 20th term is a value of 39. We know that the 8th term is a value of 75, and that's all we have. It's asking us to find the first term and then the common difference, right? So I have this gap here that I don't know about, and I have this big gap here that I don't know about. Well, because arithmetic sequences keep adding the same term over and over again, you can think of it as a constant. You can kind of interpret this as a slope formula. We can get the common difference. Here's how you get the common difference, right? We would take the term value, 39, and subtract off 75. And we would divide that by the term position, 20 minus 8. So that's going to give me negative 36 divided by 12, which gives me negative 3. Woohoo! Therefore, I know that the common difference here has to be a negative 3. Okay, great. Do I want to count back minus 3 from 8 all the way back to 1? Well, I could to get the first term, or I could also just use the fast forward formula, right? So I could say this. A sub n has to be a sub 1 plus n minus 1 times d. So a sub n, right, I happen to know that a sub 20 has a value associated with it. A sub 1 is the thing I don't know, plus n minus 1, this has to be 19, times the common difference, which is negative 3. Now ask yourself the question, what is the value of a sub 20? Well, it's given to me at 39. So 39 must be a sub 1 minus 57 when I take 19 times 3. So if I add 57 to both sides, I know that the first term has to be 96. So I can kind of work backwards. So the first term is 96, the common difference was negative 3, and I used basically a slope interpretation of arithmetic sequences to find it. Pretty cool stuff there. That's a more difficult example. So if you need to watch that one again, go ahead and pause it and go back over it. All right, here we go. Let's go to number 8 now. Let's talk about, for arithmetic sequences, you can actually find the sum of an arithmetic sequence. So add them all together, right? So the question I have here is, what does finite mean? If you don't know what finite means, it means that the term ends somewhere. It doesn't go on for forever and ever and ever. So here's what we have, the sum of a finite arithmetic sequence. So we're going to use S sub n, right? This is stand for sum of the first n terms is n over 2 multiplied by the first term and the last term added together. All right, let's use that right here. And then we'll come back to our mosaic. And I'll cook it up there. Okay, find the sum of the first 15 terms here. So here's what we want, right? A sub 1 plus a sub 2 plus a sub 3 plus blah, 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 all the way out to a sub 15. Okay, well, the formula says the sum of the first 15 terms has to be 15 divided by 2 times the first term plus the last term. Well, let's get those. A sub 1 is going to be 2 times 1 plus 3, so that looks like a 5 to me. And then the last term, 15, is going to be 2 times 15 plus 3, which is looks like 33. So I know the first term is 5, I know the last term is 33, and I'm adding together the first 15 terms. So that would have to be 15 divided by 2. The first term is 5, the last term is 33. So therefore, when I do the math, I get 285 for a grand total for the first 15 terms of this arithmetic sequence. Very important there. All right, and our last example here, back to the mosaic here. So what was your initial guess? We're going to figure out if you were close or not. So this mosaic happens to be an arithmetic sequence, right? In the first row at the very bottom here, there's a grand total of 20 tiles. You can count them up. In the next row, there's a grand total of, if you count all these up right here that I'm pointing to, of 19 tiles. In the next row, there's a grand total of 18 tiles and all the way up. There's 10 rows in order. There's 11 rows in all, and there's 10 tiles in the very last row. So here's what we're going to do. We want the sum of the 11 rows that we see. Well, that's going to be 11 over 2 multiplied by the first term. There's 20 in the first term. There's 20 tiles in the first row, and there's 10 tiles in the last row. So the sum of the first 11 terms is 11 over 2 multiplied by 30. So the sum of the first 11 tiles happens to be 165. So there are a grand total of 165 tiles in all. So, were you close? How far off were you? Okay, print these notes out, watch the video again, and come ready to work on Friday.